Hello, in the first video on negative binomial, I showed you this example where we were, like in a Ludo game, just rolling the dice until we got a 6, and that allowed us to start the game. Can't join till then. And so in this example, we just needed one success, and that's r equals 1, and this game continued until that success took place. So technically it could go on forever, and so we used that diagram to deal with it. Let's extend that idea now. What if we had to roll 2 6s before we could start at Ludo? Well, let's start making some examples of success. Well, this is the first and simplest one, that we have we roll the dice twice and we get 2 6s. So we'd be finished, wouldn't we, in 2 trials, so their n would equal 2, wouldn't it? What else could we have? Well, we could be unsuccessful the first time, fail, and then we get a 6, and then we get a 6. So we've completed this in 3 trials. Or we could be successful, unsuccessful, and then successful again. So again, that's an n equals 3, and we could carry on and do this for n equals 4, n equals 5, etc. But what would help us is to have a structure that deals with this, and what I've got below is a set of diagrams that deal with all the routes resulting in success in a certain number of trials. So first one up then, n equals 2. Well, there's only one way that we can have that happen. We've got to be successful on the first or second run. How about we're successful in 3 trials? Well, what's got to happen? Well, the last trial must be a success, yeah? So we get this sort of tail going on here. But above that, we've got 2 routes for these 2 diagrams up here, and we can combine them into a single diagram. So we could either be unsuccessful and successful, or we could be successful and unsuccessful. So we could go either way around this diamond here and end up there. So there's only 2 ways of doing that, aren't there? Now let's have a think about success in 4 trials. Well, again, the last trial must be a success, so therefore we must have 1 other success and 2 failures. And we've got loads of ways around this. We can either have the 2 failures and then the success, or failure, success, failure, or we could have success, failure, failure. So as you can see, you can go any way around that, and there are 3 ways around that one, aren't there? There's 2 ways around that, and there's 1 way around this one. So that's important. So what would happen if we start extending this diagram? Well, let's have a look at the example we had earlier, where we were successful in 7 trials. Well, again, the last trial here must be a success. So that leaves us with an extension of this sort of diamond lattice diagram, doesn't it? And we got lots of ways around here. We have to get from this point here at the start to this point here. And we could go, you know, fail, 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 success. So we could have 5 failures and then 1 success, or, you know, we could go along there, 4 failures and a success, then 2 more fails, etc. And if you have a look at it, how many ways are there through this? 1, 2, 3, 4, 5, 6. There's 6 ways through that. Then we could get it. 6 combinations, yeah? And, you know, what's 6? Well, that is our n, which was 7 minus 1, isn't it? So if we took that as a logical deduction, how many roots are there? There's n minus 1 roots. So what does that tell us about the probability? Well, like a binomial, we've got n minus ways of getting this outcome. We've got 2 successes, so I've got p to the 2, and I've got n minus 2 failures, so that will be q to the n minus 2. So what we've got now is a nice way of presenting what we're doing. Here it is in this diagram, and it's something that we can now generalize. We've got as we extend, that was for 2 successes. So here we've got our original diagram, so let's build up a pattern about number of successes now. So our original diagram was for r equals 1. There was the 1 success, there it is at the end. Our next diagram we've just done is diagrams that deal with r equals 2. And in this case, I think it was n equals 7 or whatever. But as you can see, we had a sort of one layer lattice going on here, didn't we? Again, with the success tail there. So let's reproduce that. What if we needed 3 successes? Let's have a look at this diagram then. There's the 3 successes. So what's going on here? Well, I've got a final success over here, and I need 2 other successes along the way. I'm still going from this point to that point here. So how many combinations have I got there? Well, what I'm really doing is I've got n-1 trials, haven't I? And I'm choosing where to place my 2 successes, yeah? So that means I've got n-1, choose 2 going on here as my number of routes through this lattice here. And then I've got, we said r equals 3 successes, so I've got p to the power 3, and then I've got q to the n-3. So maybe now you're starting to see what the pattern is. So let's have a look at our final view of this. So if I need r successes overall, here's one of them here, that's the final one. So I need r-1 successes in my little lattice. I'm starting over here and I'm going to here. So that's n-1 trials again. I've got n-1 and I need to choose r minus the places to put my r-1 successes. So that's why I'm getting these combinations. That's my number of routes, yeah? That's my routes. I could pick some routes here, couldn't I? Could be any old route. I could go to there and then down to there and then to there and then to there and that to there. That's a route, yeah, through this, depending on what comes up. So 2 fails, 1 success, 1 fail, 1 success, 1 fail, 1 success, 1 fail, 1 success, and 1. And there we are. That would get us from there, this point to that point. So that means that I can come up with a generalized formula for the probability here. So this is the bit that's different from an ordinary binomial where we'd have n-1, so we'd have n choose r, wouldn't we, in an ordinary binomial. Here we've got n-1 choose r-1. So why have I got a -1? Because this bit is always at the end, isn't it? It's final successes at the end. So all I'm left with is the rest of it, n-1 trials and r-1 successes. And there's my p to the r, that's the probability of succeeding r times, and q to the n minus r, that's the failing n minus r times. So there we have it. That's what our formula for our probability of a negative binomial is. Let's have a look at the diagram here of our distribution. Well, what happens here? Well, at the start, if r was 3, then any number of 4, say, any number below that, we can't be successful because we need 3 successes. So all these initial probabilities must be 0. Our first probability that's non-zero will be when we get to r, so 4, we can succeed in 4 trials, can't we? Then it moves up to a peak, where it's more likely, where our n choose r, n-1 choose r-1 is dominating. And it drops off again. Why? Well, it's very unlikely you're going to have to wait 1,000 trials to get, say, 4 successes, get 4 sixes, isn't it? So that's why our probability is going down again. Okay. Mean and standard deviation we need to have a look at. We've looked at that in the first video, so a very similar thing going on here, except we've got an extra term in here. Okay, so what's my expectation? Well, again, I've got a series. I'm going from r as being our minimum to infinity, and I've got my value of number of trials, and I've got my probability of that. So success in 1 trial, probability of 1. Success in 2 trials, probability times probability 2. Success in 3 trials times the probability of 3. And if I start subbing in these values here, we can see that we must start really with r, because all the probabilities below that are 0. So I've got r times pr, r plus 1 times the probability of r plus 1. And if I start subbing in the probabilities, well, the first one, being successful in r, I've only got one way of doing that, and my probability is I've got to have r successes, so p lots of r. The second one, I've got r plus 1 way of doing that. So I've got r plus 1 size the success. I've got this n choose r of that. I've got p to the r again. I'm having r successes. And then I've got one failure. And I'd go on to 2 failures, 3 failures, 4 failures, etc. If I just replace these n choose r's with these little simplifications here, you probably know those, then you can see that I could put into a bracket out front as factors r and p to the power r, and now I've got this series in here, which is actually a binomial expansion of 1 minus q to the power negative r plus 1. So if I know that, I could substitute that in place. I know what the binomial is I was expanding. There it is. 1 over 1 minus q, brackets all to the power r plus 1. Well, of course, that's p to the r plus 1, isn't it? So I can do some cancellation. And before I know where I am, I've got that my mean is r over p. That makes sense, doesn't it? If I wanted to get two sixes, I'm probably going to have to roll my dice 12 times, aren't I? Because I'd expect to get 6 every 6 rolls, and I need 2 of them, so that will be 12. Let's just check that that works. R equals 2 over the probability of success 1/6. That is 2 times 6 equals 12. There we go. So that's what our mean is. I'll quickly show the variance. I'm not going to spend a lot of time on this because it's quite a complicated formula, but best way to do it is for us to think of it as being e to the x squared minus the mean squared, isn't it? The mean all squared. There we go. So I'm going to find e to the x squared. So let's do that. So the only difference in the formula I had above for the mean is I've now got r squared there, and I've got r plus 1 squared, and I've got r all the way through r plus 2 squared, etc. And actually that means that I've got a different binomial expansion. And there we go. I can take some factors out the front, get this binomial here, and actually you might see that it's a differential here because I've got an rq to the r minus 1. So I'd need to integrate that and then find the binomial expansion and then solve it. So if I do that, this bracket becomes this lovely beast here. And again, I can start cancelling stuff between here and here. Before you know where you are, I've got this expression, okay, for e to the expectation of x squared. So what's the variance? Well, it's that minus the mean squared. We know that e to the x, the mean, equals r over p, so that term's going to be r squared minus p squared, r squared over p squared rather, and you'll see there's quite a nice simple cancellation where that cancels with that, and we're just left with this as a variance of a negative binomial. There we go, rq over p squared. So there you have it. That's my summary page for a negative binomial. Think of it as the grid. We've got standard probability, we've got the distribution, we know the mean, and we know the variance. Best of luck.